Patchell from Oxford, and that will be a sister algebra talk with new examples of strict compatibility.
Well, yeah, thank you very much for inviting me to give a talk. I'm glad that Emmanuel gave a talk this morning where he mentioned selflessness, so I have a lead in here. Okay, so yeah, so this is joint work with Tatamasi Amrutam, Srivatsa Kumakumale and David Gao. So let me talk about linear algebra first to kind of motivate the setup. Okay, so all right, so let's say I have two n by n complex matrices. Okay, so let's say that x is subequivalent to y if there are s and t, so that s, y, t is x. Okay, so somehow I can algebraically kind of pull y down into x. Okay. So here's a nice linear algebra fact, is that this subequivalence is exactly witnessed by, okay, so x is less than y, if and only if the rank is less. Okay. So this subequivalence is equivalent to the dimension of the column space of the matrices. All right. Okay, so this is a very nice fact, and actually in Neumann algebras we have sort of an analog of this fact using dimension functions instead of rank. Except now the rank can sort of be continuous. So what I want to talk about is what happens for C-star algebras. So there's a few issues with C-star algebras. They're not as nice as the complex numbers in general. But they're more interesting, right? Because there's more stuff that can go wrong with them.
Yeah, nearly as nice.
Yeah, that's right. So we can still define reasonably good notions of subequivalence, and actually the notions of subequivalence give rise to sort of, I guess, homological theories on C-star algebras. So this is sort of where like K0 comes from and the K1 group comes from. And actually the Kuhn semigroup is what I'll talk about in a minute, is really kind of like a super powered version of the K0 group. Okay, anyway, subequivalence is very interesting in C-star algebras. Okay? And in a lot of cases, actually, we can also define a form of rank. Okay, so let's do that now. Okay, let me give a quick primer on C-star algebras, though. Okay, so let's recall. Okay, a C-star algebra is a closed star subalgebra of the bounded operators on some Hilbert space. And there's two examples, which will be, I'll just focus really on these two examples for today. One is K, which are the compact operators on a separable Hilbert space. Okay, and these are really like limits of matrices. Okay, right? So this is literally, that's a closure of the finite rank operators. And then two, okay, if G is a discrete group, then, okay, we can take the left Rayleigh representation of G into, I guess, bounded, well, it's unitaries, but I'll say bounded operators on L2 of G. And then we define the reduced C-star algebra as, I guess I need to say this. We take the span of the image and close it up. Okay, so this will live inside of L2G. Okay, so this is our operator algebra, and really it's somehow, at least for us, it's, you know, it's witnessing the left Rayleigh representation. All right, so let's talk about comparison. And I should note that these are both, these both have traces. Okay, for compacts, you can take the trace of your finite rank operators, and then, okay, there might be ones that have infinite trace in the end. Okay, well, that's okay. And for this, we always have a nice finite trace. So what does this do? It just picks out, it's actually just the trace of identity is 1 and trace of all the other group elements is 0. Okay, so let A tau be tracial C-star algebra. Okay. And I'm going to say, okay, so take A and B to be positive elements in here. So what is this? This is really, I think of this as the closed union of all the matrices over our C-star algebra. Okay, so we want to kind of allow for some matrix amplification room. And I also want to have them be positive. And we'll say that A is subequivalent to B if there are some xn's that take B down to A. Okay, so that's our subequivalence. Okay, very similar to matrices. And we can also define a dimension function because we have a trace. Okay, so we can also define d tau of A to be the following limit. This will be tau tensor trace the nth roots. Okay. Okay, so it's good to think about why this is, the rank, right? So if A is just complex numbers, which we know is our favorite C-star algebra, then this is just really matrices. And if you have a matrix, it's a positive definite matrix, and okay, you can diagonalize it, and when you take the nth roots, all the non-zero eigenvalues will go to 1, and all the zeros will stay at 0. So this will just detect the rank. Okay, so it is the rank. Okay. Of course, it might not be integer valued anymore, but okay, if it's not C. All right, so proposition, if you have subequivalence, then you have comparison of the dimension functions. But converse can fail. And it can fail kind of for easy reasons. So for example, if you take, let's say, I don't know, M3 direct sum M4, that's a C-star algebra, and comparison will fail. Something in this component can't be subequivalent to something in this component unless one of them is 0 or something. Because there's no partial isometry to take them between. But even if you assert that your C-star algebra is simple, this can fail. So actually, even if A is simple, nuclear, unique trace, this property can still fail. Okay. This was first shown by Villadsen, I think, the late 90s, early 2000s. And actually, this was really important in the classification of C-star algebras because this is sort of telling you basically how badly behaved the K-naught group and more generally the Kuhn semigroup can be behaved. And so they sort of had to add in more stuff into the Elliott invariant, but also exclude some other examples. Okay, so it helps refine that procedure quite a bit. Okay, so historically, it's important. Okay, and then so actually, maybe I'll just define it up here. This is slightly bad board work, but okay. Okay, so we'll say A has strict comparison if the converse holds. Okay. And usually we say something slightly stronger, we actually say this is a strict inequality. And there's reasons for this. Again, historically, there's algebras where, there's even really nice algebras where if you have equality, it doesn't work. But so we say this. Okay, so then this. All right. Okay, so I was kind of alluding to how this is really important in the classification of nuclear C-star algebras. But maybe of more interest for this audience is, how can this be witnessed in, let's say, group C-star algebras? Okay. All right, so here's a...
Maybe you should avoid using the...
This word?
Yes.
Okay, I'll go back to the left then. Okay, thanks. Okay. So now you all know the title and the co-authors, right? Okay. Okay, so strict comparison was first isolated as a property in 1989 in work of Blackadar, and then in 1991, so this is Joel Anderson, Blackadar, and Hagerup. So what they found is a comparison phenomenon in a free product. So here's the theorem. Okay, so let A be the reduced group C-star algebra of Z mod 2Z free product Z mod 3Z. Okay. Yeah, the 2 and 3 are not so important. It's, as long as it's not an immutable free product. Okay, so take P, which is in sort of the left side here. So let's say it's a projection in this left side, and Q will be a projection in the right side. Where, okay, well, this is just C2, right? So there's projections that trace a half, right? Or at least one. Okay. And over here, I'll take a projection of trace 1/3. Okay. Now, what's not so obvious is, okay, well, also, because it's a projection, the trace is the same thing as the dimension function. Okay. Now, what's not so obvious is whether Q is actually subequivalent to P, right? Because they sort of live in opposite sides of this free product. So the theorem is, and there's a couple of consequences they derive out of this, but the theorem is that Q is actually subequivalent to P. Okay, so this is not an obvious or immediate theorem, but they do prove this. So this is telling us that using free independence, maybe we can find some more comparison phenomena. Okay, so, and actually there's a kind of, and this is not strict comparison of this algebra, that's not what I'm claiming. I'm just saying that these two particular projections have subequivalence. Okay, so it's kind of very specific to the setup. But now,
if you would replace the regular representation by another representation, will it still be the same?
it'll depend on the representation. Yeah. So for example, if you have kind of a very silly representation, right? If you represent, let's say into what's like quotient out onto Z mod 2Z, direct sum Z mod 3Z, then you'll fail to have the comparison.
But can you explain when, which kind of representation will still hold this theorem?
That's a good question.
That C-star algebra is simple. So
yes.
Yeah.
Yes. So it is closely tied to the simplicity of the C-star algebra. So my best guess to answer your question would be whenever the representation yields a simple C-star algebra. Yeah. So yes, good. Yes.
Are there examples of group C-star algebras that do not have strict comparison?
It depends on what hypothesis you put on. So the short answer is yes. The long answer is that's a hard question. So the short answer is yes, kind of again for the same reason. So if you have a, what am I trying to say? Yeah, so again, like with finite groups, if you have like this kind of direct sum of two finite groups, that should fail. But for more complicated things, it's not so clear. I was going to mention this at the end, but I might as well say it now. It's like what's open is whether a C-star simple group must have comparison. That's an open problem, right? So that's like kind of yeah. So the answer is I don't know.
Okay. Can I have something much simpler? I'm confused with the notation. In your definition here, you tensor down the compact operators, but you don't seem to have up there any compact operators. So what exactly do you mean?
Yes. So I guess really I mean that they're sub-equivalent, in a tensor K. But it doesn't really matter, I guess. They're also sub-equivalent in just
any compact operator, and you have that property. That's what you mean by this.
What, sorry?
You tensor on any compact operator and you have that property. That's what you mean.
I mean, so I
The
can.
definition of Q less or equal P over there in that theorem. That's what I'm trying to say.
Yes. So. Okay. I'll be more precise. I'll say it more precisely. Okay. So i.e. So actually, it holds in A itself. Okay. In this case. So i.e. There exists xn in A. So xn. And actually, it's on the nose even. It's actually equals. I think it's literally a unitary conjugate and then cut down by projections.
What is the relation with the story you just told us before? Or are you going to explain that?
Well, so here's the relation, right? So the relation is when can you go from a dimension function inequality to some kind of subequivalence, algebraic subequivalence. And this is one of the first places in the literature where this sort of thing appears. Okay, so here's another theorem. So this is due to Dijkma and Roortem, 98. And I guess technically they say do something which is slightly weaker than I'm going to say, but basically the same argument works for this. Okay, anyway, it's fine. So here's a theorem, which is that C star F infinity has strict comparison. Okay, and what's really crucial for their argument is that you have infinity here. And so what's the idea? Well, you take two positive elements. They're each sort of supported on finally many generators up to epsilon. And now they're freely independent, so then you can emulate this argument approximately. Okay, there's a bit more detail, some functional calculus, but that's sort of the main idea. But to get two arbitrary things with finite support to be in free position, you need to conjugate by another generator. So you have to have sort of arbitrarily many generators in free position to make this work. Okay. So it does work for arbitrary infinite reduced free products. Sorry, I guess it should be lambda. But sort of for even finite free products, this was not really so clear. Okay. Okay, so then, sorry, let me get oriented.
They just prove it from projections and then measure simplification.
That's correct. They did prove it for projections there, but then in 2012, so in Lionel Roberts' NCCW complex classification paper, he has the proof, credited to Roortem there, personal communication, and the proof is essentially a copying of that argument from this paper. So I'm lying slightly by saying this, but at least it has Roortem. So, okay. So I'm not lying too badly. Okay, so then sort of over the next maybe 15 years or so, strict comparison was really studied in the context of nuclear C-star algebras in the classification program. So the Thomas-Winter conjecture states that in the nuclear setting, up to a few adjectives, strict comparison should be the same as something called Z stability. Okay, and this was proven in the unique trace case by Matui and Sato in 2012. But for our story, we're going to stick with the non-nuclear setting. Okay, so I'll kind of skip most of the details there. And I'll get to 2016. Okay, so Barlak, Szabo. And then also a few years later, this is 2016, kind of in 2021, this is formalized in a slightly different way by a 6-author paper. It's Farah, Hart, Robert, Tequisis, Ignati, and Winter, which is that if you have the following diagram, okay, so by L infinity of A, I just mean norm-bounded sequences of elements in A. Sorry, my if is not done. Okay, and we have a B here, and we have this. If you have this diagram, which commutes, this is just the diagonal inclusion, and B has strict comparison, comp, then so does A. Okay. So for example, kind of write this down explicitly, and it's not a super long argument, but what this means this paper is on the model theory of C-star algebras, and what this is saying is that strict comparison is a universal existential property. Okay, so there's like a model theoretic interpretation of the class of property it's in. Okay, so this gives us a hint. So I'm kind of course, I'm presenting it like a textbook, right? It's not necessarily how people. I'm giving you the post hoc story. Okay, but.
If you replace infinity A with an order power of A, it's the same?
That's right, yes. So that's kind of something special about the normal algebra powers that you can do either. So I actually usually would write the algebra power, but I think this is slightly more accessible. But yes, the answer is yes. And I should know where this is. I think it's in Alex Sabo's paper that you can replace with the algebra power. If not, it's definitely in Robert's selfless paper that you can, but I think it comes from Alex Sabo. But I just don't remember off the top of my head. Yeah, it's the same. Yeah.
I mean, Robert just had the purpose the same. I think it's written out there. Anyway.
It's not actually written somewhere. Yeah. Okay. Yeah. Okay. Yes. Okay. So then, so based on the story, the following definition hopefully seems, well, at least feels somewhat natural. Okay. So this is Lionel Robert. Definition. Okay. So we say that A is selfless if, I guess you can say there exists phi star hom. All right, so we have A embedding into L infinity of A diagonally, and A can also embed into this free product. It's technically a reduced free product. And all right, just A embeds into itself. And then what we want to assert is that we can complete the diagram. Okay. So basically, Dykema-Rortem's result says that this thing will have comparison, because it's an infinite reduced free product. And so if the diagram holds, then so will A. Right. Okay, so let me just state that out explicitly. Okay, so then maybe a theorem or proposition. If A is selfless, will imply that A has strict comparison. Also, okay, and you get a few other regularity properties too. So you get simplicity, okay, so which is one of the things that we wanted for strict comparison in the first place to avoid direct sums and a few other degenerate conditions. If tau is actually a trace, this forces you to have a unique trace. It also forces something called stable rank 1. It's another like C-star regularity property. Okay.
Where does the terminology come from?
The selfless?
Selfless.
Yeah, I've talked to Lino about this. So the idea is, so what is this really saying? It's saying that you have, actually the way he wrote it initially is that you have a free product itself living in here instead of free product. So it's like A has a, an asymptotic copy of itself, right? So it's like, okay, it's outside of itself, or it's selfless. Okay, it's approximately what he told me. Okay, hopefully I didn't butcher the story.
What is the role of the trace in definition of selfless?
What's that, sorry?
What is the role of tau?
The role of tau? Yeah, so it does a few things.
For A itself.
What's this?
So, can you make a definition for A without tau, or
So it does two things. So one is that, so the diagram is actually in the category of C-star probability spaces, so it takes all the states to the corresponding states. So like here we have, the trace, this will have a a trace coming from the free product construction, and then this will have a non-faithful trace coming from this, the sequence trace. The other thing that the trace is important for is that we can do a reduced free product down here, get something that's simple. So if you just did a full free product, it wouldn't be simple in general, right? It'd have a whole bunch of quotients. And the fact that this thing is simple is really important, right? Otherwise, the theorem is that simple implies simple, right? Non-simple doesn't help you. Right? So hopefully that answers. Okay. Okay, so there's some natural examples that fit into this diagram. So for example, the reduced group C-star algebra of F infinity will fit into this diagram because of having these kind of infinitely many generators. Okay, so you can basically kind of push the generators off to infinity and get a sequence. Of course, that's not really so helpful, right? Because we already know all these nice properties of F infinity. Okay, so, but maybe for other groups we could kind of use this strategy. Okay, so here's part one of the strategy. Okay, so let's take a group G. Okay. Okay, so first I'll say, I'm going to do something a little bit bad. Okay, sorry. We'll say MI. Let me just write the picture. Okay. So G going into, inside of L infinity, I'll just write product G. Yeah, so one comment is that having F infinity versus having just Z there actually doesn't make a difference, as it turns out. And the reason is because you can conjugate A by sort of anything that's freely independent from it and get many free copies. Okay, so there's kind of a little trick there, and that's why I can put Z here and be fine. So having this diagram be satisfied is actually called being mixed identity free. And okay, so let's sort of okay, maybe you can sort of turn this diagram into this diagram. But the main issue is that, what are you really getting? You're getting some kind of representation of G free product Z into some really giant Hilbert space here. And what you want is that representation to be weakly contained inside the left regular. Okay. Or in other words, you want the operator norm to correspond to the reduced group C-star algebra norm. Okay, and if you just have a kind of a general map here, this is sort of a little bit too wild, and we don't really know how to control this. And actually, we now know that there are groups that are, well, I basically already did this kind of right away. There are groups that are MIF that are not selfless. So for example, there are MIF groups that are even amenable, and therefore cannot be C-star simple. Okay. So it's not really strong enough. So what we're going to do is we're going to strengthen this a little bit, and I want to say the group is selfless. And I think that's a complaint about the name, so maybe it should be like quantitative MIF, but anyway. It was called selfless in the morning, so I'll stick with that. Okay, so if this diagram, and a little bit more. So, and now I'm going to add a generating set. And the definition will be independent of the generating set, so okay, as long as it's finite. Okay. If this, and there exists a polynomial P such that, what do I want to say? There exists an element in G such that the length of G is at most P of n. I should say there's a for all n here. Okay. And for all words in here, if the word is only length n, that'll imply that W of G is non-trivial. Okay. So, okay, I said there exists a phi, but really what is this phi, right? Phi is just an assignment of this generator to a sequence. Okay, so you just think of, for each n, I get an element. Okay, so maybe being slightly facetious here. Okay, all right, so this G is really phi of z to the n. Sorry, no, phi of z, the nth term of the sequence. Okay. Okay, so this is some kind of quantitative control, right? It's saying that if I have some kind of non-commutative word in the group, I take all of them of some fixed length, then I can refute it with one element, which is not too big. Okay. Oh yeah, don't use that word. Okay.
Sorry?
Yes.
The comment you made before about this not being enough because there's some amenable groups. So are you saying that amenable groups, even if they're MIF, they will not have this property?
There probably are some that have this property too. So this is still only half the story.
Okay.
But this is set up to plug in with the other half. Yeah, okay. Yes. No, sorry, that was a bit misleading. Sorry. Okay. All right, so actually this is one of the theorems that we proved in our paper. Which is that if G is acylindrically hyperbolic, and has something called a trivial finite radical, okay, so it gets rid of some kind of trivialities. Then the group, just as a discrete group, is selfless. And our bound is something like O of n to the 12, or maybe it's 14, I can't remember. It's something large like this. It's not a pretty proof, but it worked, and we were very happy with this. And since our paper came out, which is going to have the application, there's been a number of expansions of this. So Bradford and Sisto showed that the same, except you get O of n. Actually, they show something even stronger. So they show that for a fixed word of length n, you can refute it with a logarithmically large group element here. And then that turns out to be sufficient to get the uniform version. And they do it using a completely different method. So they use it doing a kind of random walk technique. And then on the linear group side, there were also a number of recent / upcoming results in this vein. So Itamar Vigdorovich earlier this year showed that if G is a co-compact lattice in PSLD K for K a local field. Then G is selfless. And then there's this upcoming work of Avni and Galander. So Avni, Galander, and I guess Becker and Briard also have even a beyond version of this. Okay, so I haven't seen the draft. Okay, so hopefully I'm not misciting the. So you please correct me if this is inaccurate, but I think the theorem is something like if G is linear and MIF, then G is selfless. So the quantitative bit is automatic. course, the results are stronger than this, but this is one particular application. Okay, so this is only half the story. So this is somehow like the algebraic picture. But I mentioned earlier we still have to calculate some kind of operator norm. Okay, so here's a definition. Okay, so a group G has rapid decay, or RD. Actually, let me bookend this discussion quickly, is just that finite rank free groups are definitely in this class.
I think the right condition instead of MIF is no immutable radical.
Oh, just trivial immutable radical.
Yeah.
Okay. And is it equivalent actually for linear groups, or no? Anyway, it doesn't. It's not part.
It is equivalent to C-star simplicity. So yes.
Okay. Okay. Thanks. Okay. Yeah. I think I saw a draft of this one, and they just said MIF. I think in the theorem 1.1. So that's why I put it there. But yeah, I think okay. Thank you. Okay. Okay. So a group G has rapid decay. Okay. This will be the analytic part. Okay. If there is a polynomial Q such that if phi is in the group algebra and phi is supported on words.
It's not free from the definition of MIF.
What's this?
It's not free from the definition of MIF.
No, this is different. Yeah, that's right. Yeah, would you like me to use a different letter? That's okay. Okay, that's right. Okay, on words of length at most n, then the operator norm of phi is at most q. At least I use a different polynomial. Okay. Okay. Let's q then times the 2 norm. Okay. Okay. Well, okay. Good thing my diagram's still there. So why would this potentially be useful? Well, in this diagram up here, this actually naturally extends to a diagram of the group algebras, and all the maps are injective, and they're trace preserving, right? They're state preserving. So they're actually 2 norm isometries. So if we have some sort of rapid decay phenomenon happening, then we can say something about the operator norm. And it is the upper bound that we really need here. All right, so maybe some brief history here. So just maybe examples. So Hagerup in '78 showed that free groups have rapid decay. And then De La Harpe in '88 showed this for hyperbolic groups. And then I think it was actually it might have been Julie Saint who actually coined the word rapid decay. I think up to this point it's just called Hagerup's inequality. Yeah, okay, so in, wait, I guess we can say this too. Okay, so Kahn and Moskovich, yeah. I think this is 90. Use this to use RD used for the Novikov conjecture. Running out of space. And then I'll also say, I guess, Joliet in 90 proved RD for certain amalgamated free products and extensions. But I think you basically need finite amalgams or kind of finite index extensions because it's a little bit tricky. In 98, there's 3 authors: Ramagi, Robertson, and Steger. Sorry, 98. You do RD for certain lattices in non-Archimedean fields. I guess, was it like? It's stated in a bit of a weird way. Okay, so what is it? It's like, I'll say SL3 of, I don't know, K for K non-Archimedean. And then, okay, before it did this for an Archimedean field, okay, RD for co-compact SL3R. Okay, so we're into this. We're into the setting of linear groups. That's nice. Okay, not just Fn. Okay, and then actually Laforgue also in O2 use RD for the Bon-Kahn conjecture. Okay, and then I'm going to skip way forwards from 2002, and I'm going to say that actually rapid decay sort of made okay, well, I mean, it was still studied in between, but I'm going to mention a modern result. So this is the result of Lauder and McGee. This is from 2022, I believe. So what they do is this is not just showing RD for a group, this is applying RD to a problem. Okay. So they use rapid decay to show strong convergence for limit groups. All right, so then actually seeing this argument, okay, so limit groups are groups that are related quite closely to free groups. And strong convergence is a asymptotic operator norm estimate, which is what we also needed for our C-star algebras problem. Okay, so we actually have all the ingredients now to state the main theorem. Okay. Okay, so here's the theorem. Okay, if G is selfless and has rapid decay, so these two pieces together, then the reduced group C-star algebra is selfless. Okay. Okay, so we were happy with this, and then kind of combining known results on rapid decay and the results I mentioned of Utamar, Apicalander, Becker, Brouillard, and Bradford Sisto, and then ourselves. This gave kind of a big class of groups whose reduced group C-star algebras were selfless. Okay. So for example, all hyperbolic groups, including all the finite rank free groups, or I should say hyperbolic with trivial finite radical, but also basically all linear groups that happen to have rapid decay. So for example, the co-compact lattices in SL3R will fit into this class. Okay, so since then, the question is sort of, can this be pushed beyond this class? Is this an if and only if condition? And we know now that the converse is definitely not true in general. Okay, so let me state this as a problem. So I've sort of given you kind of the, here are some sufficient conditions. And then earlier I gave you some necessary conditions. So the algebra has to have strict comparison. These are C-star algebraic conditions, but you need to have strict comparison, have to have simplicity, have to have unique trace. And so here's some implications. So we know that, so this selfless implies this is strict comparison and simple. And of course, this implies that the algebra is simple. But actually, both of these backwards implications are open. So we actually don't know if there's any gap between these. I said this earlier. Right? Yeah. Okay. Maybe one quick remark is that strict comparison does not imply simplicity. And actually, in a follow-up paper to this, Raum, Thiel, and Villalta showed that there are groups that have strict comparison that aren't simple. And what you can do is you can take basically selfless group. You can take groups that are sort of almost selfless that have rapid decay. So what you can do is, for example, take hyperbolic groups that have a non-trivial finite radical, and this will work. You might need something slightly more than this, but it's approximately the strategy. Okay. And maybe I should make a remark. So this is a deep result of Briard, Kalantar, Kennedy, and Ozawa. Okay, so this is Briard. So what they did is they were able to characterize C-star simplicity. Okay, so C-star, this guy is simple. If and only if G admits a strongly proximal boundary. What's that, sorry?
It's already Kalantar on the Kennedy.
Oh, it's a Kalantar Kennedy. Oh, but you guys right, you do a bit more because you do the unique trace property too. Yeah. Okay. Thanks. Sorry, I was too generous. Yeah. Okay. Okay. So this is a dynamical condition on the group, and it turns out this is also equivalent to like kind of more concrete, you could say maybe intrinsic properties of the group. And okay, there were a whole bunch of equivalent versions that were discovered in this time. So, with your permission, Taka, I'm going to mention a couple of your recent results, if that's okay. So recently, Taka put out a paper with some very different sort of sufficient conditions for selflessness. So let's mention two of these. One. So if G has an so-called extremely proximal boundary, then this thing is selfless. Oh, that's right. I forgot. That's very important. Well, I guess boundary includes free, right? Okay. We can say it's topologically free. Okay. In my head, boundary included the word topologically free, but anyway. Okay.
It's only possible.
No. So I'm thinking of boundary as action on a compact space, which is topologically free and minimal. Yeah. And then the proximality changes. Okay, so that's why the adjective there changed. Okay, well this actually is not a necessary condition because extremely proximal will imply MIF. Okay? And there are things that are not MIF that are still selfless. So here's an example. Okay, so if G and H are exact, as their C-star algebras are exact, and their C-star algebras are selfless, then this C-star algebra will also be selfless. So why is this? This is actually, to me, a really fascinating result for the following reason, and maybe I'll end with this last comment. So. So here's the comment, which is that so G times H is never selfless as a group. Okay. As long as both G and H are non-trivial. Okay. So here's the proof. Really easy, actually. So what do we need? So it suffices to find some word in here such that W of, well, I guess G comma H is identity for all elements in the group. Okay. So, I mean, selfless as a group, right, requires that this is non-trivial with even control, but I'm going to claim this is not possible at all. And it's actually quite easy. So, okay, so just take G and G non-trivial, and H and H, and then we can just take W to G. G, okay, it's a bit long, but bear with me. Okay, G inverse X, H inverse X inverse. Okay. So because we're in a product group, all the products split out and everything will cancel. Okay. That's the whole proof. Okay. So this is really fascinating, right? Because what this is telling us is that in the C-star algebra framework, we have more going on, right? You know, we have kind of selflessness can come not just from group elements, but sort of from the algebra structure itself. Okay. So this is kind of I don't know, it's definitely a less well studied phenomenon than mixed identity freeness for groups. And it's kind of a different phenomenon. And as my problem suggests, it's really, we have a lot of open questions still. Okay, I think I'll stop here. Thanks for listening.
I do have a question.
Yes, of course.
It seems the second statement, can it be expressed as a general statement about exact C-star algebras and tensor products?
Yes, it can, yes. That's right, yes. So, the theorem is, if A and B are exact and selfless, okay, so the states also, then the min tensor is selfless. That's how I'd state it for groups. That's the focus.
Questions? Okay.
Yeah.
It's clear from here, but it's still. What's the status for non-compact lattices for SF3Z?
Great question. So I think.
It doesn't have RV.
This I know.
Yes.
Of course you know.
Yeah. So I think the selflessness is unclear. Yeah.
It does not have an exclusive proximity.
Good question. No. Not an obvious one.
Yes.
That's right.
No questions? The last chance. So the segregation.